today's session in microcomputer systems. I have already shared my screen, but before we start with the topics, one remark or one wish from my side, because yesterday in the second lab, in the physical lab, I've seen that there were only around about 10 students, not more. And there were a lot of empty seats. And in the last week, the group was much bigger and the lab was really overcrowded. So the last week, there were too much students in the lab, and we cannot keep distance, and it becomes warmer and warmer in the room. So maybe it's possible for some of you that you switch from lab group 1 to lab group 2. I've put in the e-learning this group schedule where you can register for a specific group. In the e-learning, it looks good, but in reality, most of the students come to the first session. So therefore, I kindly ask you check your schedule, and if it's possible, then switch to session 2, that we get an equal distribution between the two groups. That's better from the pandemic perspective, but also better from the teaching perspective, because then I can talk to all of you and we can try to solve the exercises together. If there are so many students in the lab, then it's hard for me to talk to everyone or to help everyone. It's not possible. Unfortunately, I'm not Agent Smith from Matrix, and I'm not able to fork myself. Therefore, it's very hard to serve all students if there are a lot of people in the lab. So maybe it's possible for you to change the group. Did they change the name of the course? You see the cover sheet, right, from the lecture notes already. No, we didn't rename it. That's in the end, because this course is based on the German class, and in the German class for BMC and for BET in the curriculum, it's called Mikrocomputertechnologie und Informatik 2, and therefore that's a direct translation. So you can strike through the title here and can write down microcomputer technology. You are in the right class. No rename. Everything is fine. Google Übersetzung, right? So no, we have, to be honest, we have a translation service, but the translation service, of course, did not check curriculum or organizational things. Simply, the translation service simply does a plain translation, and then it's up to us as lecturers and to students to fix the points that are not correct. So you are in the right class, microcomputer technology, microcomputer systems. And today I will start with the second part. The first part, we have short repetition. In the last week, we have talked again about finite state machines and how to declare or describe them and how they can be implemented. And yesterday in the virtual Zoom lab, we have already done one exercise sheet or half of an exercise sheet for finite state machines. And we will also cover this with the physical labs in the next weeks. So stay tuned. There will be an exercise also for finite state machines. And today we want to do, or I want to give you an introduction to the second part. As in the last semester, I have reused the lecture notes from my colleague Heinz Endres, and therefore here some short acknowledgements to him. And yes, you can also see the entire version of the lecture notes contains 200 slides or 200 pages. And these 200 pages are for a class with 4 hours per week. So that's too much for us. we cannot cover all topics. Therefore, I will select chapters that are very interesting from my perspective and important for you. And I always give you a hint, okay, this is not relevant for the examination. That doesn't mean it's not relevant at all, but I will only cover or ask topics in the examination that we have discussed here together. Yeah, so take some notes on your copy, on your PDF, which slides are important and which slides are in addition to the topics that I will not check in the exam. The slides on the e-learning have 8 chapters. 8 chapters, I think so, right? Maybe I've uploaded a newer version of the lecture notes, but there are only some smaller changes. If there are even more slides, then you can be sure that we will not cover this. So you will recognize a lot of the slides I will show you here. And the topics that we are not discussing, you can simply ignore it. Yeah. Of course, feel free if you want to study this too, then you can do it, but it's too much content for 2 hours per week. Therefore, I reduce it and I focus on, from my perspective, the most interesting parts. And this is changing over the semesters. So if you have already attended this class, maybe in the past, if you are a redoer or something like this, then you should be aware that the contents for this semester can change. Yeah? So you should also listen and be here in this semester. We will see. We will see. We're doing the foundations, and then we will see if we cover memory modules, modern architectures, and so on. Yeah? I decide during the class. Okay. So we have to stay flexible. Okay. Perfect. Then here a short outline of the contents of this class, what we want to discuss or what I want to present to you. Today I give you a short introduction, why we talk about microcomputers at all. Yeah, they are today standardized and everywhere. Is this still a topic? And I hope I can give you some motivation or introduction why this is interesting. And in the second chapter, we will study the principal structure of a microcomputer. So we want to understand how smartphones, tablets, PCs, servers, workstations, whatever, how they are constructed and how they can be operated, how they are working. Because the overall system layout, the overall structure is the same for all of these components. There's one small exception if you have very specialized hardware at home, very specialized hardware for a very specialized use case. Then maybe there is another construction approach, but we will also cover the different approaches in chapter 2. Yeah? So we'll talk about SISD, SIMD, MISD, and NIMD constructions, and I give you some examples which layout or which approach suits best for a specific use case. Then we have one real-world example here, a big real-world example in chapter 3. That's our Infineon XMC series board. That's one example for an ARM-based microcomputer. I'm sure that you have read a lot about ARM microcomputers in the last month due to the fact that Apple at the moment makes a transition from Intel-based processors to ARM-based processors. They have introduced their first ARM-based processor for Mac in March of this year, right? I think so, half a year ago. Yeah, so that's the Yeah, you're right. That was a good decision, right? It was a good decision. They have a lot of experience in the design of ARM architectures because they already use ARM architecture in their iPhones, and they simply transferred this simply in quotation marks, right? They simply transferred this to their mobile architecture, and they got a lot of good grades, a lot of good feedback in the literature regarding power consumption, regarding overall speed of the system. November 2020. Okay, thank you. So November 2020. Okay, time's running. Okay, 1 year ago. Okay, nearly 1 year ago. So, but the overall step has been done, and yeah, Intel at the moment is really struggling to keep the pace with this performance, and I think this will be interesting in the next month and also in 2022. And yeah, we will see. And maybe you have seen this also in the media. The next release of ARM-based hardware is on the next Monday. Yeah, so I'm very interested what will be presented. New hardware, ARM-based M1X or something like this, as the shortcut for the processors. We will see. And here in chapter 3, we will take a look at one experimental board and on the instruction set for this Infineon ARM core. So I will show you the complete instruction set from the original manual, from Infineon. We can use this in this class. That's very good because Heinz Endres, my colleague, during his time in industry, he was an employee of Infineon, and therefore we can also use this material and we can cover this topic here. So you get a real detailed view into how to program ARM-based hardware. So you get an idea what can you give as statements, how are the statements interpreted, and how to work with this instruction set. Yeah, then we have the real-world example, but the real-world example, to be honest, it is a very complex example because it's a real processor with a lot of functionality, a very sophisticated instruction set. Therefore, that's very complex. So you have to revise the lectures to keep up with the topics. And an easier approach to talk about instruction sets is shown in chapter 4. That's my favorite chapter, to be honest, in this part of the class, because in chapter 4 we will construct our own 8-bit, 4-bit microprocessor. So we design from scratch with all components the complete microprocessor. Then we define our own instruction set. And then in the lab, we will write some assembler code. So all of the coding we're talking about here is in the end assembler coding. And then we will write some assembler code in the lab to solve specific problems on our own hardware. And yeah, you will see that between our instruction set and the ARM instruction set, there are, of course, big differences. And I hope you will also understand why you can solve specific problems with the ARM instruction set, but not with our own instruction set. So I can also, I will always ask, or I always asking in the exam, okay, is this problem solvable? Can you give an implementation for the solution on this set, on this instruction set, or in this instruction set? And then you can show if you have understood the differences, how to program and implement in assembler. you want to know, Gadi, what's assembly or what's assembler coding, what this term means, right? Assembler coding means in the end that you give the instructions, the statements directly to your CPU, So you have no higher level programming language like C++ or C or whatever, what you prefer, but you directly implement on the hardware. You directly give the statements that can be executed on the hardware. We will see that's very hard to use because in the end you have only zeros and ones to express the problem, but we will then switch to mnemonic and then we will talk about mnemonic coding. Okay, let me see a lot of remarks in the chat. Sounds like a lot of fun. I hope so. I like the content. Never been this excited for you. So now you have raised the level, right? Saying if you are very excited, I have to deliver. Now it's very hard for me, but I do my best. I do my best. Okay, yeah, no problem. If you have not joined the online lab session, I will also make the solution visible. And in the next week or in the next session, we go ahead also with the finite state machines exercise sheet. So you have missed one session, but that's not the end of the world.
Excuse me, so I have a question. The final exam this semester, is it going to involve the content from last semester plus this semester, or the content from mainly this semester?
Both semesters are contained. Okay. But I decide for each exam where the focus is on. Sometimes I prefer more exercises from the first part. Sometimes I prefer more exercise from the second part. Sometimes it's 50-50. It's up to me, and you have to prepare everything. Okay.
Okay. Thank you.
So we will see. We have a lot of topics. I can make an exam for 5 hours, but we have only 2. Therefore, I have to select exercises, and yeah, you have to prepare everything. Okay. Then in chapter 5, we talk about process control via interrupts. This is also interesting because interrupt handling. Maybe you have already seen this on your Windows machine, on Apple hardware, on a Mac. Interrupt handling is not so interesting because the drivers plus the hardware plus the operating system comes from one vendor, from one company, and therefore I never ever have to adjust interrupts on my Mac hardware, but I've modified interrupts and work with interrupts on my Windows machine. So maybe that's interesting for you, because if you go in your system control, I think it's called system control in Windows, then you can manage which hardware component uses which interrupt. And here in this class, I try to explain, okay, what does it mean? What is interrupt? Why we need it at all? Yeah? And how can we configure or use interrupts? And as good advice, if all interrupts work perfectly on your system, don't touch it. Because if you get a mess with your interrupts, then your system gets really buggy. But it's possible in Windows. You can modify interrupts. If you have old hardware, for example, some measurement tools, then sometimes you have to fiddle around with the interrupts in your system. Yeah, and in chapter 6, here we talk about some codes for representation of data. We talk about different characteristics of codes. So we talk, for example, about the Hamming distance, or the fact that a code can be used for error detection, maybe even for error correction. So you need specific mathematical characteristics that you can find an error or that you can fix an error. So this is also a very nice chapter, because here we can use, or we can study some of the basic codes that were used in the real world. So for example, we talk about CRC, that's cyclic redundancy checksum. Maybe you have seen this if you download an image, DVD image. Today you will not download much images, but if you download a software tool from GitHub or something like this, and you want to check that during download the tool has not been manipulated and there is no malware in your tool, you can use checksums, and we will talk about these checksums and how they work here in this class. And I also show you how to calculate checksums on your system. I can show you this on my Mac. It's very easy, but it's also possible in the same way on Windows. Maybe you have already used this. If you prefer security on your system, then you always work with this checksums. Saeed, do you have a question? Close your microphone. Oh, okay. Good, then let's start with a good old introduction. So first chapter is always introduction. A short historic overview about microcomputers. We will not cover all slides. I will outline the most interesting parts here, the most interesting topics here. We start with the bibliography, with some textbooks that you can use, or feel free to use them. I've already said in the last semester, everything you need you will find here in the lecture notes, but sometimes it helps if you read some additional texts from additional authors, maybe then you get a better understanding or a new perspective. And we talk about application of microprocessors in microcomputers. I will show you market sharing. Market sharing is always outdated. If I put something on a slide, market sharing, and 4 weeks later, market sharing is outdated, but the main players and the main KPIs are still valid. So we can take a short look on this. Then we talk about historic development. Where did we start? And you will see, if you ask a US American, he or she will tell you, we have invented the computer. And if you ask a German, then he or she will say, we have invented the computer. And both are correct. Both are correct, because that's not only true for computers, but for all scientific developments. You have parallel developments in different countries. All scientists work on similar problems, and then there is a point in time where everybody gets a solution, maybe in parallel, and then there is no I'm the first or I'm the second. So oftentimes you get comparable or equal solutions from different scientists. So in Germany, we always say Zuse has invented the computer, and in the US, United States, there are several other scientists that also invented the PC, and everybody has the right to state this. It's okay. Yeah, and then we talk about some terminology that we need throughout this class that we will use in the next weeks and months. Hello. Questions? Oh, okay.
No, Professor. It was by mistake. I'm sorry.
No problem.
Okay, thank you.
Okay, so goal of this lecture: getting to know the structure, functioning, components, programming, and practical application of microcomputers and embedded controllers. I've already told this during our start. And above all, having lots of fun. That's of course true. Yeah. So studies can also be fun. I hope you have already recognized this during your semesters. Yeah, some topics for or what we will cover in the next weeks. We today talk about fields of application, history, and then in the next week or in the next 2 weeks, we cover different classifications for microcomputers. We cover different architectures. We talk about the hardware components within a microcomputer. We will talk about periphery. So everything, peripheries, in the end, everything outside of the CPU. So everything that's connected via an interface or via a bus system to your CPU, that's periphery. Then we will see, okay, how does instruction set look like? We will see instruction set for ARM, as I've said, and the instruction set for our own CPU. We do some programming. I hope I get it organized that we can also do some reprogramming on the boards in the lab. I have to organize this with the lab engineer. I hope this works. But of course, we will do some programming with pen and paper. And in the Excel, you will not get some experimental feature or experimental tool. You will get pen and paper, and then you have to write down the instructions to solve a specific problem. We have again some exercise sheets, and at the end of the class, we take some outlook on future work, future trends, future architectures. At the moment, quantum computing is in the media. So Google said 2 years ago, we've got a real quantum computer, a real quantum PC, but then nothing happens. So they announce that they have it, that they can use it, and then there should be an acceleration in the development or in the tools, but nothing happens. So we will see if they really have a quantum computer that works, and maybe we'll talk about these trends at the end of the class, maybe before Christmas, as a small Christmas lecture. Here the literature that you can use. Again, we have some German books if you want to also learn the language, to study in German. And we have some English books. And I don't read now the authors. You can simply search for these books in our library, or you can use our online portal to make to borrow the books online. So this is possible, but as I've said, everything that you really need to get a good grade, you will find here also in the lecture. So it's only an addition if you want to deepen a specific topic that's interesting for you. Subsection 1.2, application of microprocessors and microcomputers. I tried to outline what I'm talking about. Let me see if this works. Perfect. So here on this slide, we find a lot of different fields of application where you can find a microprocessor or a microcomputer. We haven't defined the difference between microcomputer and microprocessor up to now. We will do this in a few minutes, but here on this slide, you have a summarization of all possible fields of application. So this is the most obvious one, office computers and devices. So that's our daily life. So you will find these components in your keyboard, in your mouse, in your monitor, in your screen, in your scanner, in your graphics card, in your hub, in your router, in bridges, in photocopier, and so on. So all devices in your office, home office, or at FAWS uses some kind of microprocessor, but also your home electronics. There are a lot of microprocessors in use. So maybe you have a very sophisticated washing machine, not only warm and cold, but more programs for specific clothing. Then you have a microcomputer to drive and to control the entire machine, your dishwasher, your microwave oven, your coffee making machine, your TV set, your heating, all of these use in the end microprocessors. Or if you will think about some measuring instruments, smart measuring instruments, like the oscilloscopes in the lab. Now, the oscilloscopes in the lab use a microprocessor. They have an interface, they have a front end that you can use to store data, to read data, and so on. Spectrum analyzers, test systems, scales, measuring bridges, all of them maybe use a microprocessor. Samsung Smart Fridge is practically a computer. So this is a fridge, I guess, that will order new butter if you have consumed everything, right? Something like this. A big screen, and you can look inside the fridge, and then you see, oh, I need new beer, for example. Something like this. Yeah. Twitter on fridge, okay. Yeah. That's everything is possible. You can put a microprocessor everywhere. For example, also, this is this part here, industrial automation or automation of buildings. So here in Germany at the moment, it's very famous that you enhance your home, that you try to implement a smart home, and you put microprocessors in the light switches, in the doorbell, everywhere. And there are a lot of nice applications, but I have one problem. For example, if you have a blackout in your area, then you are not able to leave your house, and that's a problem for me. So I don't want to recognize or to feel that there are microprocessors around me. So in computer science, this is called ambiguous computing. So everywhere should be computer functionality, but you should not recognize it. And at the moment, I'm not sure how the current state of automation in foreign countries look like, but in Germany we are still on the way. So we are putting PLCs in our homes and try to automate our homes, but we at the moment generate more problems than we solve. So for example, we cannot simply switch on the light. We first have to implement that a switch can switch on the light, and that's too much for me. I simply want to press the button and then it should work. So Twitter on a fridge, maybe that's possible, but I can also take the beer out of the fridge without Twitter. So yeah, it's a use case, but it's necessary that you want it, that you accept it. Tweet it on Samsung Smart Fridge or something like this. Okay. Yeah, here are further fields of application. I think most of them you have already used or seen. And yeah, you can imagine everything needs, in the end, integrated circuits, microcomputers. And if the supply runs out, if there are no more chips, no more integrated circuits like in the moment due to the Corona crisis, then all of these sectors, all of these industries will get a problem. So in Germany at the moment, we have problems to manufacture our cars. We are big car sellers. We sell our cars to the entire world still. And yeah, at the moment there are no chips, therefore we have to reduce production. So that's in the end really a problem if we're running out of supplies. Okay, here's the market share that I've already mentioned in the beginning. The numbers are already outdated because they are from first quarter of 2016. but in the end, it's interesting if you look here at the top five manufacturers for semiconductors: Intel, Samsung, TSMC, Broadcom, and Qualcomm. And before our class, I've read that TSMC gets a tremendous gain due to the fact that Apple buys at TSMC, and stock almost doubled. Yeah, correct. Yeah. So who has stocks from TSMC? Who's rich now? $300 per share in June last year. Now it's almost 600 US dollars. Okay. Okay, but with crypto, you're not talking about hundreds of US dollars, but millions, right? So then you were laughing about TSMC. Okay. But so we don't have to talk about the numbers here because they are outdated, but you see the main players in this game, the main manufacturers for semiconductors. TSMC, now very high rank, maybe 2 or 1, maybe before Intel, I'm not sure. Intel and Samsung, Broadcom, Qualcomm, and then a lot more. And Infineon, that's a German company, therefore is also Infineon. It's not one of the biggest players, but it's still there in this ranking top 20. And at the moment, maybe you have read this, at the moment we try in Germany to get more independent in the supply chain from the semiconductor manufacturing, because at the moment we cannot manufacture because we have no materials, no semiconductors here in our own country. Therefore, we try to get more independent with our own plants. And at the moment, Bosch tries to establish their own semiconductor manufacturing. They open their own plant also during the Corona crisis. So I'm not sure if this was the last year or this year, but they try also to give some, so to say, foundation that we need to realize our systems. But of course, we still need the components from Intel, TSMC, and so on. So there are so much components, so much systems that need semiconductors. Therefore, Bosch cannot fix this alone, but it's a good approach that we get more resistant to errors in the supply chain, like during the Corona crisis. Okay, so now we take a look at the historic development. Where did we start with microcomputers? And then we go step by step to most recent approaches to design and use microcomputer. We start in 1642 with Pascal's mechanical calculator. Calculator is maybe too much because it's not a calculator that you know from your desk. It's simply used for addition. So to speed up addition, there was a mechanical calculator. Mechanical means no current, no voltage, nothing like this, but the calculation was done by switching real physical switches in the end. Then 30 years later, there was Leibniz mechanical calculator. This calculator also offers multiplication and division. And with this mechanical calculator by Leibniz, there was also the introduction of the binary number system. Binary number system, that was our first lecture in the first class. And You see, the binary system is really old, yeah. But if something is used for so long duration, you can be sure that's an error-free system. Yeah? You can use it also for the next 100 years. I increase my volume here. I hope that helps. Gregory? Better now? I hope so. I speak, and if you cannot, no?
For the audio is coming through fine for me.
Okay, for Adam it's fine. Okay, then I speak slowly, and I hope your connection line fixes itself during the session. Sometimes it helps. Okay. That was Leibniz mechanical calculator, and then in 1842 there was the Babbage analytical engine. That was a real milestone in microcomputer construction, because we have for the first time a so-called arithmetic logical unit. You can, if you want, double underline this term, because this ALU, or in German we simply call it ALU, ALU, this arithmetic logical unit. This is one key component within your CPU, and we will also construct an ALU, a very easy ALU, but you will get the overall approach. So we've got an ALU for arithmetic and logic operations, and we've got a separated memory. This Babbage analytical machine was able to process 30 digits, so small numbers in the end, only 30 digits. And the execution was driven by a programmed algorithm. So loops were possible, and conditional jumps were possible. So everything in the end that you know from your programming class. So conditional jumps mean that you can use if else and then execute a specific sequence of statements depending on a condition. And looping means in the end that you repeat the commands until you have reached a specific condition. Then, nearly 100 years later, SUSE starts to work, or starts to publish and realize his work. From the German perspective, this was the invention of the first digital computer based on relay technology and vacuum tubes. So the first computer uses vacuum tubes and relays, and the main problem was that this old construction approach was very fragile. So if you have 100 vacuum tubes, there were always 10 vacuum tubes broken. So the system never really works because the vacuum tubes were so fragile. And we will see on the next slide that the invention of the transistor and the construction of the first transistor fixed this. So the transistor becomes the base component as an electronical switch within all PCs, within all computers today. But before or during the Second World War, these machines were constructed based on vacuum tubes. And vacuum tube gate, yeah. And who of you are playing retro games, point and click adventures, maybe? So maybe you know, I'm not sure, you are really not so old like me, but maybe you still know LucasArts games or Lucasfilm games. They made a lot of very good, no, not like Doom. Doom is an eco shooter, right? I also play Doom, but I mean point and click adventures where you have to solve riddles. Monkey Island, exactly, yeah. And you have to move your avatar around, and then you can say, take a hammer from that, use hammer with nail. So you have to solve riddles, you have to solve problems. And this is retro gaming, point and click gaming. Today, you find a lot of these retro games. And I'm telling you this because there is a very nice game, a retro game called Thimbleweed Park. And this is a remake or not a remake, but it's a retro game in the style of Monkey Island or Indiana Jones or Sam & Max or something like this. And it plays in a parallel reality to our reality, where everything is automated by microprocessors, but all of them use still vacuum tubes. Yeah? So there are no transistors because transistors are bad and they not really work. And you can walk around, and all systems, all PCs are driven by vacuum tubes. And of course, they are always broken. So if you want to use a PC, you have to find the specific vacuum tube to use this PC. Yeah. So it's in the end a joke. Yeah. So the programmers were geeks or nerds, and they have simply created a parallel reality that is still based on the vacuum tube approach. But you can see here, or I've told you that vacuum tubes, due to the fact that they are very fragile, they have been replaced by transistors. But SUSE's first approach, his first digital computer was based on vacuum tubes. He called this machine SUSE 1 and SUSE 3. So he really liked his own name, right? Yeah, SUSE 1 and SUSE 3. And yeah, we have again our ALU, our arithmetic logical unit, and we have a control unit that was separated from the memory. We will also construct a control unit in a few weeks. And this machine supports 9 instructions: plus, minus, multiplication, division, square root, in, out, read, and write. That's it. So you have to try to solve all problems only with this 9 instructions. But you can also use conditional jumps, and these conditional jumps are realized or has been realized by gluing together punched tapes. Maybe you have you ever seen a punched tape? Maybe maybe in a museum or somewhere. Yeah, a punched tape is in the end a tape of paper, and in this tape of paper you can put holes for, to be honest, I don't know, I think a 1. And if there is no hole, then it's a 0. So you have to implement your programs as a sequence or a scheme of holes and non-holes on this sheet of paper. And if you want some conditional jumps, you simply glue together these pieces of paper. And to be honest, for myself, I never ever used this. But during my studies, I can remember my operating systems prof, a very nice prof, I've learned a lot in his class. He told me that during his studies, long time ago, yeah, fairy tales, long time ago, he has still implemented his programs with punched tapes. So he sat in his flat in his room, and he implemented the program by punching holes in the tape, and then he takes the entire hole, the staple, the hole, the tape staple, and put it to the Rechenzentrum, So the central processing, there was one central processing in the university, and then the program has been executed. And if there was an error, everything goes back to the student, and he has to find, okay, which hole is not correct in this program. So there were no PCs at home. So today you power up your PC, you open your IDE, you start programming. If you have a problem, you ask your prof. The prof says, okay, do this, do that, no problem. But if you have to prepare your programs physically on a punch tape, you can imagine you have to be very precise. Otherwise, you never ever get a running program. Yeah? So I only know this from fairy tales from the past, but I can imagine it's not so funny like today. So today you can try and study everything very easy because you have the hardware on hand. You can directly start. You don't need this central processing and this physical processing. And if you stay in Munich, I hope so you can do this during your studies here in Germany. I've also lived there for a few years, a very nice city. Then you can also visit not only the bars and the clubs, but you can also visit the German Museum in Munich. And there you can see the Z3, the SUSE 3, as the first digital computer. So I've seen this Z3 a long time ago during my studies. I'm not sure when I've been in Munich in the German Museum, but it's very interesting. And next to this digital computer, you will also find a mechanical one, a mechanical computer based on a binary system. And this binary system is realized via some flutes in some boxes. So you can open the box and the flutes is flowing out, then it's a 0. And if you fill in flutes, then it's a 1. And everything is realized via flute routing in the end. So that's very interesting. LMU, what do you mean? Where should I look? Do you mean the university, or what do you mean with LMU? Yeah, that's Ludwigs-Maximilian University, and there is a second one in Munich, Technical University of Munich. So you will find 2 universities in Munich. But the German Museum is independent, I guess. So that's a separate organization you can visit. So it's open to the public, and you can take a look at this very old hardware if you're interested. So after clubbing, go to the German Museum. So then in 1944, so you see the biggest steps were done during the Second World War. So the biggest steps in microcomputer development were between 1930 and 1950, something within this range. Yeah? And maybe you have already heard in other classes, of course, this development was driven, unfortunately, not by public demand, but by military demand, because maybe you have heard about Enigma or something like this, so some cryptographic applications. So this is oftentimes the case that the military demand drives the civil usage in the end. Yeah? So the internet is an outcome of the DARPANET, and DARPANET was a decentralized net invented in the US that should survive a nuclear blast. That is the idea of the internet. Yeah? So the DARPANET was designed in a decentralized manner with decentralized nodes that can still communicate if you nuke one node, so for a nuclear blast, and then the remaining system still works. And out of this idea, the modern World Wide Web appears. Yeah? So that's unfortunately the case. And my guess is because for military application, there is more money. That's sad, but I think yeah, that's true. So oftentimes, if there is some crisis in the world, this also boosts the technical improvement. So if you compare this with Corona, for example, so here in Germany, we really done a digitalization boost during the last 2 years because we have to. The computer used to work with a clock frequency of 5 to 10 hertz. Wow, yeah, that's correct. So the technical parameters, today you laugh about this. So 5 hertz, 10 hertz, but back in this time, everybody was happy that this can be realized. We will see in a second some additional technical specs, and then you will again laugh. Yeah. So 1944, there was the Icon. That was an electromechanical computer for the decimal system. It's what was called Mark I. Maybe you have already heard Mark I, Mark II, Mark III. Where did you heard this? Mark I, Mark II, Mark III. Iron Man, exactly. So, so Stan Lee also was a computer geek, I think so. Yeah? So the suit of Iron Man is Mark I, Mark II, Mark III. Yeah? He starts with a very a big suit that needs a specific changing room to use it. Yeah? And in the last movie, it was based on nanotechnology. Yeah? He simply presses the button in his breast, and then the nanoparticles creates the suit. Yeah, rest in peace. Yeah, that's right. Yeah, Tony Stark gives everything for the universe. So, but maybe you will see. Yeah, you know, in the Marvel universe, superhero never ever dies. Yeah, so we will see. But Mark I, Mark II, Mark III, and so on, I'm sure that goes back exactly to these systems, and yeah, the script writers were also computer geeks. Yeah. Sound like you like Iron Man? No, I'm not Iron Man. I like Iron Man. No, I like Iron Man. So okay, that was the Mark I, developed in Harvard, yeah, one of the most famous universities out there in the world. Simultaneously to the SUSE computer, and 6 seconds per multiplication. Yeah? So you enter your multiplication with a very complicated program, you press execute, and then you count to 6, and then maybe you get the right answer. Okay, we have to stop this Iron Man discussion because then it's hard for me to give the lecture. Okay, but yeah, maybe. Yeah, it was good. But I think Iron Man really looks better than me. For this case, I cannot be Iron Man. So 1947, we have the Icon, that was Mark II. And please note here the gain of performance between Mark I and Mark II. Because the Mark I needs 6 seconds per multiplication, Mark II 0.7 seconds. So we have a real performance boost within 3 years, only 3 years. And that's, we will see in a few minutes, that's unique for the computer industry and for computer science, that this performance boost, this performance gain over the time is tremendous. If we have realized this for cars, for example, then today you can drive 10,000 kilometers with 1 liter of gasoline. But you know that's not possible, and we will never ever reach this. But in computer technology and microcomputer technology, this tremendous gain of performance and functionality, it's really cool. Yeah, really cool. Yeah, here is a picture from the first computer bug that was found by Grace Hopper. Here, born 1906, died 1992. And yeah, here you see, it's hard to read, but you can see here is the mnemonic code or the assembly code to execute in calculation. And here at this position where the relay and the panel F is used and something like this, there was a bug, and this bug has been marked. And this is so famous, this example. You can see this in the National Museum of American History in Washington. So this sheet of paper with the algorithm, and then posted with, here is the bug, you can see in the National Museum. So yeah, you can see here there were no debuggers, there were no tools. You simply write down your program on a sheet of paper, then you transfer it to the binary encoding in the system. And if you have done an error, you recognize after execution, you have to go back to your paper and you have to check, okay, where is the real problem? Now you can also read here in between that you have to start the cosine tape. So that's about the calculation of cosine. And then you have to change the tape, and something goes wrong with this tape. There was a bug, and the bug looks like this, you know, back in the old days. Okay. So last slide for the historic development. Now, 1945, we get the ENIAC from Eichen, Eckert, and Mochlin. That was this machine was also based on vacuum tubes. It consumed 150 kilowatt of energy, and per edition we need 200 microseconds. So this is really fast, not from the perspective of today, but for this time that was really, really fast. We have 20 registers. You can also underline this term registers because we will use it a lot during this class. A register is a memory cell within your CPU. That's in the end the memory cell that can be driven with the highest frequency, so the system frequency. You know, your PC at home has a system frequency of 4 gigahertz, for example. But this 4 gigahertz are only used or are only applied within the CPU. And all memory cells within the CPU can be driven with this maximum clock speed. If you leave the CPU, if you go to your main board or to your secondary memory, then the clock frequency is reduced. We will see why, but the clock frequency is reduced. So the system gets slower if you are not located within the CPU, and registers are the memory cells with the highest frequency and therefore the highest speed. So registers, very important. Does it store data before they are sent into the CPU for execution? Correct. Yeah. So the registers are, so to say, a buffer where the CPU can store data for calculations. That's the buffer located directly next to your CPU, to your ALU, within your CPU.
Professor, I have a question. So Professor, when you talk about this term registers, are we talking about like base frequencies? Is this, if I understood it correctly? Because all I know is that, for example, if you have a particular class of processors like the Comet Lakes in Intel, which is, I think, i9, it has a base frequency of 2.8, and then it boosts up to 5.2. Is that what we're talking about, or have I lost the plot?
No, that's correct. So this base frequency, or the highest frequency that can be used to drive your system, is used to drive the ALU, the control unit, and also the registers. So this 2.8 gigahertz or multiples of this can only use within the CPU and the components within the CPU. If you leave the CPU and you look at the mainboard, the periphery, whatever, then the speed is reduced. So you need very fast memory cells next to the CPU, and these memory cells are called registers. So take a note, register equals memory cell driven with highest frequency, with system frequency. Okay, each register has a width of 10 decimal digits. So the registers can store different width of data. So 4-bit, 8-bit, 16-bit. We will see in a second for which system this is true. And the ENIAC was programmed via wiring. So if you want to implement a new algorithm, you have to rewire the entire system. Very error-prone and, of course, very time-consuming, because you cannot add a logic via software and the software is executed, but you have to rewire the hardware. You have to change the hardware to solve a new problem. That's crazy from today's perspective. You never ever will open your PC and soldering around in your PC or do something like this to solve a new problem. You simply update the software and then you have another application, another solution. Yeah? But back in these days, there was no operating system, no software-based algorithms. The algorithms were realized in hardware. Yeah, then 2 years later, 1947, there was the discovery of the transistor action or transistor effect at Bell Labs. Bardeen, Brattain, and Shockley were the scientists that make this possible. And based on this transistor effect, so in the end, based on the idea of an electronic switch that can be opened or closed, we will see in the next years, or we have seen in the next years, so-called UNIVAC or UNIVAC 1 and the IBM 701 and 702. And here on the right side, there is a picture of the first monolithically integrated transistor. So integrated, it's still a big piece of hardware, so not comparable with today's integrated circuits with nanometer production size. But yeah, this was the beginning. It was the beginning, and this was also the replacement for our vacuum tubes. So here, the parallel reality of Thimbleby Park ends, and we are now in our reality. You know, maybe there are several realities, but in our reality, we use now this monolithic, this transistor effect to drive or to construct our PCs. And since 1960, we have a lot of integrated circuits based on the transistor effect in mainframes. So these old mainframes have cryptic names like CDC 66,000 or UNIVAC 6, IBM 360. You don't have to memorize this one. VAX workstation. There were still some old VAXs at my university, but you don't need to memorize this. 1971, we have seen the first monolithically integrated microprocessor. Here is a picture of this, of an Intel 4-bit i4004. It looks exactly like the ICs you have seen in the lab that you can put on the breadboard. This is an integrated, full-fledged microprocessor with all components that we will study in the next weeks, completely integrated on one chip, on one IC. Here are some technical specifications. 2,250 transistors. So today we are again smiling about 2,000 transistors, where we have thousands of millions of transistors. We have a clock frequency of 740 kilohertz. And so today that's not our washing machine anymore. So the washing machine has more kilohertz than this first integrated IC. Okay. So, and now we come to more recent developments in microcomputing. On this slide, no, on the next one, there's my first PC, for example. So if you check here, we have 2 blocks. We have one table with 8-bit processors. 8-bit means that within one clock cycle, 8 bits can be processed. So numbers up to 2 power 8 bits can be processed within one clock cycle. And 60-bit processors, of course, process 16 bits within one step. And today, your system, your home PC offers a 64-bit processor and a 64-bit operating system. So within one step, 64 bits are processed within one step. And here are some examples for these old systems. So, for example, this 88, this processor, I've studied this processor at my college. During my college time, I've seen this processor in an experimental board, and we have used this from Intel. It was an 8-bit processor, and we did some assembly programming. Yeah? So the release year was 1974, and this is still used today in very easy systems because that's so cheap. Yeah? So you can simply use an 8080, you put it in, then you get base functionality of a microprocessor, and it simply works. Here are some examples for 16-bit processors from Intel. There was the 80X series. Here's the 8286. That was the first machine where you can play Doom on. Some of you, I think Sam have mentioned Doom in the chat. So the first Doom has been powered by or can be run on a 8286. This processor is from 1982, and there were several releases of one series. So there is not only one 286, there are several versions with different clocking speeds and different transistors, different number of transistors. So here this first one only offers 25 megahertz. So yeah, nearly nothing. Yeah. And my first PC is here. That was my first PC. The first version has been released in 1985. So that was not my first one because here I were 4 years old. Then I played not with a PC, but I've gotten 386 with 40 megahertz. I think 40 megahertz. And for the Intel series, for these old Intel processors, you were able to increase the system frequency by pressing a button, because there was a small button on the front of your PC, a so-called turbo button. So if you press the button, then you get a scale up of your base frequency by 1.5 or something like this. And you can imagine, never ever, I have not pushed this button because I need the speed, yeah. So I don't know why is there a button for increasing the clock speed. Of course, I always increase the clock speed if it's possible. Yeah, I do it. And for the power consumption, that was not a problem because my parents were paying the bill, right? So therefore, push the button, no problem. Yeah. Overclocking of the 80s, correct. Yeah. So there is no turbo button anymore today. Maybe in some retro PCs or something like this, some own manufactured PCs, but back in these days, you can simply overclock by pushing the turbo button. Turbo buttons just boost fans these days. You can adjust the fan speed from, it sounds like a vacuum cleaner, down to you hear nothing or something like this, right? Jet engine. Okay, jet engines. Yeah. So this was my first one. I was always sad because I want to buy an 486. That was the premium line, but unfortunately, I only got a 386. Then also AMD comes into play during the 90s. Oh, not here, AMD during the 90s with their first processors. And the first Pentium has been released in 1993, the Pentium or Pentium 1 by Intel. And this processor by Intel was very, very famous. Do you know why? Everybody knows the Pentium during this time.
Was it a multi-core processor?
No, I think the first one not a multi-core, but no, also not 64 bits. Yeah, that was also new, you're right. But there was a problem with the ALU, and this Pentium, the first version, has problems with floating point operation. So if you have done a floating point operation under specific conditions, then the ALU fails and you get a wrong result. And then in all newspapers, in the news, in magazines, everywhere, Intel has built a processor that's not able to calculate with floating point numbers. So it was a big fail. Yeah, today you will find this on Failblock or something like this, a big fail, because there was really an error in the ALU, construction error, and hardware error that cannot easily be fixed, and then you get problems with the floating point numbers. For real-world applications, for 98% of real-world applications, never ever you have recognized this error because in the digit number 20 behind the decimal point, there was a problem. And for real-world applications, so calculating with money or something like this, you never ever need this precision. So only for very, very sophisticated applications where high precision were needed, you get a problem with this Pentium 1. But yeah, today you would call this a shitstorm, right? Someone recognized this calculation error, and then a shitstorm was there, and over weeks, even in the daily news, and it was a hard time for Intel. But you cannot remember it, so for you it's not relevant anymore, and I can still remember this. Then there was a lot of new versions for this Pentium, Pentium Pro, Pentium 3. AMD offers an Athlon, a Phenom, and here we got a new naming convention from Intel. Then they call their processors Core iX. So there is still today a Core i3, Core i5, Core i7, Core i9, I think. And did you know why Intel used this scheme with I and then a number, IX or IN? It does not depend on the iPhone. If you guess this, it's another reason. Why i5, why i7? yeah, that was the marketing slogan, Intel Inside, right? But that's not the reason. But a good guess. Yeah, good guess. Intel Inside. Yeah. No, there is another reason. The reason is that it sounds cool. Yeah, it sounds cool, and it sounds especially cool for US citizens because there is a German car brand, BMW or Beamer. Do you know BMW, Beamer? And BMW or Beamer is also very famous in the US, and BMW labels his cars with also this leading eye here. So you can buy an i500 or something like this from Beamer, from BMW, and because the US citizens like this brand, this car brand, the marketing, the sales department of Intel said, okay, then we use a similar naming of our processors. Maybe that helps selling them. Yeah? It's a marketing strategy. Yeah, so 5,000 IQ. Yeah, so it depends on the Beamer. Yeah, so the German cars give the name for Intel processors. I think that's a little bit funny, right? So there's no interconnection between cars and processors, but it sounds nice. Therefore, we simply reuse it. That's the reason why we talk about processors.
Professor, I have like a general question. So for example, when we talk about these i7s or i9s till these Comet Lake processors, so they have something like 10 cores and 20 threads, which was the last one, I think i9. But now the new one, the Tiger Lake processors, they have fewer cores and fewer threads, but they perform better. Yeah. So what's up with that? Like I don't understand. First of all, the cores and threads, and what are they doing right now?
Yeah, you're right. In the beginning, the performance gain has been realized by simply doubling cores or increasing the number of cores. So they add more hardware, so to say, to solve the problems. And this not scales to infinity. You cannot simply increase hardware, and then the performance is also increasing, but there is something like ceiling. And that's, for now, that's too much, but there are problems in computer science you cannot solve with more hardware. There are problems out there, so-called NP or NP-complete problems that cannot be solved, or that cannot be solved in a polynomial time by simply increasing the hardware. So there is a mathematical reason why you cannot solve these problems by doubling hardware components. And therefore, you need better architectural approaches. So you need, for example, parallel processing, you need pipelining. We will also talk about pipelining here, that you execute several steps in parallel if possible. Or, for example, that you make random execution of commands, so that you have a so-called branch prediction. Maybe you have read about branch prediction, because 4 or 5 years ago, there was again a big arrow in the press created by Intel. Branch prediction, in the end, tries to predict what's the most probable way your program will take during execution. So if you have a program, it's not executed from the first line to the last line, but you have a lot of branches within your program, if else, if else, if else. And the branch prediction, that's a very sophisticated tool, and it's also in the end a secret, because that's the unique selling point of Intel, this tool will predict, okay, what's the most probable execution thread path in your program. And then it executes this path. And if during execution, the real execution differs from the prediction, it simply redos the work. So if the prediction is correct, you save time. If the prediction is incorrect, it's not a problem, you simply calculate it new. And these techniques, this leads to more performance. But they are very sophisticated, and only the, so to say, the principal approaches are discussed in literature, because the realization, that's the unique selling point of the processor manufacturers.
Right, Professor. So, for example, Professor, if they like say in the marketing or whatever it is, when they say that the single core performance of this chip, for example, is better, they have these scoring points. That means the branch prediction methodology of that particular chip is much better. Is that what it means?
Yeah, in the end, they have a new feature, branch prediction or pipelining, and this leads to the performance gain.
Okay, because this time Intel, I mean, I think everyone knows this, but AMD was very challenging. It was challenging Intel in the market.
Yeah.
This single core performance, and it's relatively a cooler chip.
Yeah. I'm not sure how's your opinion or of the group. So what do you prefer today? Would you say I buy an Intel chip, or would you say I buy an AMD chip? Who says, raise your hand, who says I prefer Intel? 1, 2, 3, okay, 4. Okay, 4, 5, okay. And who prefers AMD? That's Intel at the moment, right? Intel? Okay. Okay, then, of course. Okay, and now, once again, who prefers AMD? Okay. Yeah, it's nearly half-half, right? So it's not so clear. The decision is not so clear. So then if you say, okay, we have some Intel lovers, so to say, and we have some AMD lovers, and it's half-half, something about this, then AMD has really gained some market share, because I can remember 10 or 15 years ago, there were also AMD processors, but the customers prefer Intel. And not really because Intel was better or faster or whatever, but Intel offers, so to say, the original instruction set. So the first PCs offer an x86 instruction set, and Intel offers this original. It's a safe choice, exactly. So that's, of course, 100% compatible to all tools. And AMD is 99%. And this 1% where the instruction set differs, sometimes make problems. And then the customer said, no, I prefer Intel. But today, in this class, it's not representative, but we are 45 students. We have half-half. And then AMD has really gained some market share, or some market share. That's interesting. That's interesting. Okay. Yeah, let's see what's on the next slide. Yeah, last sentence on this slide, and then we start over with the details next week. Moore's Law. Moore's Law describes the development of microprocessors over time. And as you can see here on the x-axis, we have the time in a 5-year scale. And on the y-axis, we have a logarithmic scale the number of transistors. So we have 1K, 10K, 100K, 1 million, 10 million, and so on. So this scale is logarithmic. And Moore stated in his law that the number of transistors on microchips doubles about every 2 years. So every 2 years, the number of transistors can be doubled, and therefore, of course, the performance and the speed can be increased. And this law is still true. So it's possible to add more transistors to a wafer, and the wafer is the base component where the CPUs are extracted from, by simply reducing the structure size. At the moment, we use 7 nanometers as structure size. So by reducing the structure size, we can put more switches on the same area, and therefore we can operate, or we can process more steps and therefore gain performance. And this law is still true. So we can reduce the structure size, but at the moment we reaching the ceiling. So we reach an upper limit, because the smaller the structures are, 7 nanometers, the smaller the structures are, the higher is the risk for a short circuit between the components. Because if the components are so small that there is no space in between, then the probability for a short circuit increases. Also, the heat increases, so the component becomes hotter, and then we are running into physical problems. So at the moment, it seems that we will reach the ceiling in the next years, and this, you as a consumer, as a user, you will recognize this, because the clock frequency of today's PCs is not increasing anymore. So the last 10 years, you buy 1 gigahertz, 1.5 gigahertz, 2 gigahertz, 3 gigahertz, 3.6 gigahertz. But this increase of clock speed, it does not go, so it is reduced. Yeah? So we need more time to realize this increasing clock speed. So it's not possible anymore. We cannot reduce the structure size. We're running into a physical upper limit. And we will see how long Moore's law is still valid. At the moment, we're getting saturated, and we get a problem that we will reach this upper limit. We will reach the physical limit before 2030. So in 8 years, okay. Vacuum chamber computers. Yeah, okay, that's of course an idea, but then of course it has to be very expensive too. Okay, so that's all for today. We are at the end of the session. I hope you have enjoyed. In the next week, we will go ahead with more internals. Today was a warm-up, and next week we will see how the microcomputer internally looks like. Okay? Then thank you very much. Bye-bye. Tschüss.